Welcome, students. In this video, we are going to study the concept of joint densities. So far, we were interested with probabilities concerning only a single variable of interest. However, in many cases, we would like to find probabilities related to the case when we have several variables of interest. Thus, in this section, we are going to study the concepts and tools for working with distributions related to several random variables. In a specific case, when we'll be working with probabilities related to two random variables simultaneously, that case is called as bivariate densities. As in a case when we were working with single random variables, we differentiated between discrete and continuous probability density functions. We are going to do the same in joint case, and we are going to start by looking at definition of discrete joint PDF. So we have a sample space where our random variables x and y are defined. Then a joint probability density function of x and y is defined as follows. So P of xy is equal to probability of such outcomes small s in our sample space, such that random variable at that outcome small s is equal to value of small x, and random variable or at that outcome small s is equal to small y. Now let's take a look at the following example. So we have a supermarket with two express lines. Let random variables x and y denote the number of customers in the first and second lines respectively. So the joint PDF of x and y is summarized in the following nice table. Let's find probabilities that the number of customers in those two lines differs exactly by 1. So the joint PDF of x and y is summarized in the following table. For instance, if I'm looking for probabilities that we have 2 customers in the first line and 2 customers in the second line, then that probability is equal to 5%. All right, so let's find this probability here. Then this probability is equal to the sum of the following probabilities. Probability that we have 0 customers in the first line and 1 customer in the second line. So 0, 1 plus probability that we have 0 customers in the second line and 1 customer in the first line. Plus probability that we have 2 customers in the first line, 1 customer in the second. Similarly, 1 customer in the first, 2 customers in the second, plus probability that we have 3 customers in the first, 2 customers in the second, plus probability that we have 2 customers in the first line and 3 customers in the second. All right, that should be it. That should conclude all such outcomes. Then we need to calculate the following sum. Probability that random variable x is equal to 0 and random variable y is equal to 1 is given as 0.2 plus probability that we have 1 customer in the first line and 0 customers in the second, also 0.2. Plus 2 customers in the first line, 1 customer in the second as 0.055%. The same for 2 customers in the second and 1 customer in the first. and plus probability that we have 3 customers in the first, 2 customers in the second is 0.025 plus 0.025. All right, so this sum gives us 0.55. So there is a 55% chance that the number of customers in those 2 lines is going to differ by 1. Now let's take a look at the following example. Suppose 2 fair dice are rolled, let x be the sum of the numbers showing and let y be the larger of the 2. Then if we are looking for probability that random variable x is equal to 2 and random variable y is equal to 3, then there are no such outcomes, and that probability is equal to 0. If we are looking for probability that random variable x is equal to 3 and let's say random variable x is equal to 6 and random variable y is equal to 3, then there is only a single outcome where we have number 3 on both of the dice. So that is going to be equal to 1 over 36. The whole joint PDF is represented in the following table here. Now, so for instance, probability that the sum of the faces showing is equal to 7 and probability that the larger of the 2 faces equal to 4 is equal to 2 over 36. There are 2 such outcomes. First outcome is getting number 3 on the first day and 4 on the second. And the other outcome is getting 4 on the first day and 3 on the second. All right, so our PDF is summarized here. Now let's pay attention to the row totals and column totals represented here. So row totals here represent the PDF for individual random variable x. For instance, if we are looking for probability that random variable x is equal to, for instance, 6, then we have to simply sum up all values in the row when x is equal to 6. So probability x is equal to 6 attains non-zero values for the value of random variable y equal to 3, 4, and 5. So this sum here is equal to 5 over 36. Let's check whether that is true. The outcomes that will produce me a sum of faces showing equal to 6 are following. 1 on the first die, 5 on the second, 2 on the first die, 4 on the second, 3 on the first, and 3 on the second. Then 4 on the first die, 2 on the second, and finally 5 on the first day and 1 on the second. So there are 5 such outcomes. So this is 5 over 36. The individual probability for a single random variable x in that case has a special name known as marginal PDF. And if we want to find individual PDF for random variable y, we have to simply sum up all our values in columns. Thus, to find marginal PDF of random variable x, we have to sum up our joint PDF of x and y over all values of y. And to find marginal PDF of y, we have to sum up our joint PDF over all values of x. Now let's consider the case when our random variable of interest, let's say x and y, are continuous random variables and we are searching for their continuous joint PDF. Like in a case when we're working with a single random variable, in a continuous case, we know that probability is that random variable x attains some specific value, let's say a, is equal to 0. Now, in a case when we are working with bivariate distribution, bivariate continuous distributions, that will also hold true. So probability that random variable x is equal to a and random variable y is equal to some value b will also be equal to 0 for all values of a and b. Now, in a case when we were working with a single random variable, to find probability that random variable y lies in some interval, let's say from a to b, we had to integrate its PDF function in that interval from a to b. In other words, we found an area under the probability density function of that random variable x. Now, in a bivariate continuous case, we'll be looking for probability that our random variables x and y will lie in some region of x and y plane. Let's call that region as big R. Then to find that probability, we'll have to find the double integral of joint PDF of x and y. Such that x and y lie in that interval R. All right, now if we extend our plot of PDF from a single variable case to a case when we are working with two random variables x and y, then we'll have a following plot. So in z-axis here, we'll have a value of function of PDF of x and y. In x-axis, we'll have values of random variable x, and on y-axis here, we'll have values of random variable y. And let's assume that we are interested in finding probabilities that x and y lie in some region R here in red on this xy plane here. In a case when we were working with a single random variable, PDF is represented as a curve. Now, in our bivariate case, a PDF will be represented as some surface over the xy plane. So let's denote it here as this purple surface. So obviously it can extend infinitely. And now if we are looking for probability that random variables x and y lie in some region R here, then we are looking for as in continuous case we were looking for an area. Now in bivariate case we'll be looking for a volume. Volume under our surface represented by PDF of x and y over the region R here. So let's draw that. So probability that random variables x and y lie in that region R is found as a volume under our surface represented by PDF of X and Y, and above that region in red in XY plane. And from calculus, we know that to find the volume under a curve, we have to find the double integral of that PDF X and Y. Since we're looking for a volume above region R, we'll look over the values of X and Y such that they are in that region R. Okay, now let's take a look at the following example. In a case when we were working with a single random variable, PDF is represented as a curve. Now, in our bivariate case, a PDF will be represented as some surface over the XY plane. So let's denote it here as this purple surface. So obviously it can extend infinitely. And now if we are looking for probability that random variables X and Y lie in some region R here, then we are looking for as in continuous case, we were looking for an area. Now in bivariate case, we'll be looking for a volume. Volume under our surface represented by PDF of X and Y over the region R here. So let's draw that. So probability that random variables X and Y lie in that region R is found as a volume under our surface represented by PDF of X and Y, and above that region in red in XY plane. And from calculus, we know that to find the volume under a curve, we have to find the double integral of that PDF X and Y. Since we're looking for a volume above region R, we'll look over the values of X and Y such that they are in that region R. Like in a case when we're working with a single random variable, for of X and Y to be a valid PDF, we'll need the following two conditions to hold. First of all, it should be non-zero, so f of x, y should be greater or equal than 0 for all values of x and y. And we'll also need a volume under all of our surface for all values of x and y. So let's say from minus infinity to plus infinity for y, and from minus infinity to plus infinity for y. So we need that integral to be equal to 1, meaning that volume under all of our surface over all xy plane should be equal to 1. Now let's solve the following problem. Suppose that the variation in two continuous random variables x and y can be modeled by the joint PDF f of x y equal to c multiplied by x multiplied by y. For region in xy plane, y greater than 0, less than x, and x is less than 1. So first, let's draw that region here in our xy plane. So we are looking for the region in the following box from 0 to 1. If we draw the line y equal to x, then this is our line y equal to x. And we are looking for values x greater than y in that box from 0 to 1. So our region then is represented here in black. Now let's find the volume under our PDF f of xy. So it is calculated as, so first let's integrate over y, our PDF. Boundaries for y will be from 0 to this line here, y equal to x. So let me show that. So from y equal to 0 to y equal to x. And boundaries for x will be from 0 to 1. Then this double integral is equal to, so let's factor out c here, from 0 to 1. Then we'll have integral from 0 to x of s of xy. Then when integrating that, we'll hold x as a constant. So we'll have y squared over 2. From 0 to x. These are values for y. From y equal to 0 to y equal to x. So this is then equal to c. Now let's substitute y equal to x. So we'll get x cubed over 2 minus when y is equal to 0, that product is going to be equal to 0. So we'll integrate from 0 to 1, x cubed over 2, which is given as c multiplied by x to the power of 4 over 8 from 0 to 1. So this is equal to c over 8 then. And our volume under our PDF should be equal to 1. So this value should be equal to 1. So the answer is C should be equal to 8 for this f of x to be a valid PDF. Second condition is that our PDF should be non-negative, and it's going to be non-negative for positive values of C, and our C is equal to 8. So for this to be a valid PDF, C should be equal to 8. A study claims that the daily number of hours, X, a teenager watches television and the daily number of hours Y he works on his homeworks are approximated by the following joint PDF. Let's find the probability that a teenager chosen at random spends at least twice as much time watching television as he does working on his homework. So let's quantify that statement here. So at least twice as much time watching television. So number of hours watching television is represented as X, as he does working on his homework, which is represented as Y. So X should be greater or equal than 2Y. So he spends twice as much time watching television as he spends on homework. All right, now let's draw that region in XY plane. So let's draw x is equal to 2y. So this line here is a line for x is equal to 2y. Now x is greater than 0 and y is greater than 0, so we'll be looking for region in the first quadrant. For values of x greater or equal than 2y, or y less or equal than x over 2. So that will be region in black. So this is our region R. Now let's find area under our PDF and over that surface R, over that region R. So we look for double integral, and the values of y will be running from 0 up to this line here, x over 2. So this line is y is equal to x over 2. And values of, so this is from 0 to x over 2. PDF is given as xy e to the power of minus x plus y dy. And values of x are running from 0 to infinity. So from 0 to infinity dx. Okay, now to find that integral here, we'll hold x as a constant. So then we can write this down as 0 to infinity e to x multiplied by e to the power of minus x integral from 0 to x over 2 y e to the power of minus y dy dx. To find that integral here, we have to integrate it by parts. So u is equal to y, du is equal to 1 then, dv is equal to e to the power of minus y, v is then equal to minus e to the power of minus y. So then this integral here is equal to an integral from 0 to infinity x e to the power of minus x uv minus y e to the power of minus y minus v du. So this is plus integral from 0 to x over 2 of e to the power of minus y dy. Boundaries for that is from 0 to x over 2 and dx. So that is equal to integral from 0 to infinity of, so substituting x over 2 here, we'll get minus, so let's write it down in brackets first, minus x over 2 e to the power of minus x over 2. When y is equal to 0, this is 0. So now this integral here is minus e to the power of minus y when x is equal to, when y is equal to x over 2, that will be e to the power of minus x over 2. When y is equal to 0, that will be 1, so plus 1 dx. So next we'll have to find the full integral from 0 to infinity of minus x squared over 2 e to the power of minus 1.5x minus x e to the power of minus 1.5x and plus x e to the power of minus x dx. So let's find every summing term here individually. So first we are going to find this integral here. Integral, let's factor out minus 1 over 2 x squared e to the power of minus 1.5x dx from 0 to infinity. So u is equal to x squared, derivative of that is 2x, e to the power of minus 1.5x. Integral of that is 2 minus 2 over 3 e to the power of minus 1.5x. All right, then this is equal to minus 1 over 2 x minus 2 over 3 x squared e to the power of minus 1.5x from 0 to infinity minus u dv, so that will turn into plus integral from 0 to infinity 4 over 3, let's factor it out, 4 over 3 x e to the power of minus 1.5x dx. Now this is equal to minus 1 over 2. This term here will disappear if we take limit of x squared over e to the power of 1.5x. E to the power of 1.5x will grow faster, so this is 0. When we substitute 0, we have a product by 0. And this is here, again, we have to use integration by parts. So we have 4 over 3 integral from 0 to infinity x e to the power of minus 1.5. This is to the power of x, a small typo, dx. Using integration by parts again, derivative of x is 1, e to the power of minus 1.5x. Derivative of that is minus 2 over 3, e to the power of minus 1.5x. So minus 1 over 2 multiplied by 4 over 3 minus 2 over 3. UV is x multiplied by that. So e to the power of minus 1.5x from 0 to infinity minus integral of v du is then plus 2 over 3 integral of e to the power of minus 1.5x dx. All right, now we have minus 2 over 3. That term will go to 0. We have x over e to the power of 1.5x as x approaches to infinity. And when we substitute 0, this is 0. So we have 2 over 3 multiplied by minus 2 over 3 e to the power of minus 1.5x from 0 to infinity. So I would like to calculate this part separately since we are going to need result. We are going to need this result since if you recall, we also have to calculate an integral of that. So we are already doing it here. Okay, so we have minus 2/3 minus 4/9. When we substitute infinity, that is 0. When we substitute 0, this is 1. So we get 0 minus that, so it will have a plus sign. Okay, so the answer is then 8/27. And integral of x e to the power of minus 1.5x. So this term here is then given as 4/9, positive 4/9. So that term is then minus 8/27. This term is positive 4/9, so minus 4/9. And finally, we have to calculate that last integral here again using integration by parts. Derivative of x is 1, e to the power of minus x. Integral of that is minus e to the power of minus x. So this is then, we have uv x minus x e to the power of minus x. So we already know that this will go to 0. And plus integral e to the power of minus x dx from 0 to infinity. So this is equal to minus e to the power of minus x from 0 to infinity. If we substitute infinity here, we'll get 0. Substitute 0 is 1, so this is 1. All right, so then our answer is 1 minus 8/27 minus 4/9. So this is a probability that a teenager chosen at random spends at least twice as much time watching television as he spends on doing his homework. Okay. Similar to the case when we were finding marginal or individual PDFs from joint PDFs in a case when we were working with discrete random variables, we'd also be interested in finding marginal PDFs for continuous random variables. In a discrete case, if we had a joint PDF of random variables x and y, then to find marginal PDF of x, we had to sum over all values of y. Now, in a continuous case, we have to integrate over all values of y to find marginal PDF of x. Obviously, we have to integrate our joint PDF function. So here is the following definitions. And to find marginal PDF of x, we had to integrate from minus infinity to plus infinity our f of xy dy. All right, let's take a look at the following example. So we have two random variables x and y. Their joint PDF is given as 1/6. X in range from 0 to 3, and y is from 0 to 2. So let's find marginal PDF for x. Then marginal PDF of x is equal to integral over all values of y. Y lies in range from 0 to 2 of our PDF dy. So 1/6y from 0 to 2. So the answer is then 1/3. Joint CDFs. In a single random variable case, CDF was defined as a probability that our random variable, let's say x, is less or equal than some value, let's say a. Now we can extend that definition for a case when we're working with two random variables or to a bivariate case. So joint cumulative distribution function of random variables x and y is defined as probability that first random variable x is less or equal than some value u, and second random variable y is less or equal than v. So let's take a look at the following problem. We have to find joint CDF given join PDF of random variables x and y. So to find CDF, then we are looking for probabilities that x is less or equal than u. So boundaries of intersection for x will be from minus infinity to u, and simultaneously probability that y is less or equal than v. So boundaries for y is from minus infinity to v. 4 over 3 x plus xy dy dx. Now x lies in interval from 0 to 1 and y lies in interval from 0 to 1. So we can change our lower boundaries here to zeros. First, integrating by y, we have 4 over 3 xy plus 4 over 3 y squared over 2 multiplied by x. So 2 over 3 x y squared from 0 to v dx. When we substitute, so these are for values of y. So when we substitute 0, we'll get 0. So we have to integrate the following function, 4 over 3 vx plus 2 over 3 v squared x dx. All right, so we have 4 over 3 vx squared over 2 plus 2 over 3 v squared multiplied by x squared over 2. So that will be 1 over 3 v squared x squared. Boundaries are from 0 to u. Now this is equal to 2 over 3 u squared v plus 1 over 3 u squared v squared. Factoring out 1 over 3 u squared v, we have 2 plus v. So this is our CDF of random variables x and y at point uv. Now let's show the intervals where our CDF is defined. Now here, before we proceed, we have to be a little bit careful here. We know that our joint PDF of x and y has non-zero values only in interval for x from 0 to 1 and for y from 0 to 1. Now outside of this box here, our PDF has 0 is equal to 0. So our CDF will be equal to this function in interval for u from 0 and 1 and y or v from 0 to 1. In a case when u is less than 0 or v is less than 0. And now let's take a look at one of these cases. Let's assume when x is less than 0. If x is less than 0, then we know that since our PDF is equal to 0 outside of that interval, it will be equal to 0. So then if we're looking for probability that, let's assume that u is less than 0. If we are looking for probability, let's say -2, and let's choose a normal v, let's say 0.5, then we're looking for probability that x is less or equal than 2, and y is less or equal than 0.5. And now since our joint PDF is not defined when x is less than -2, so this will have a 0 probability, so the whole thing here will have a 0 probability. So in a case when u is less than 0 or v is less than 0, our CDF will be equal to 0. Now our CDF should be defined everywhere. Now let's consider the case when let's start from u being greater or equal than 1. If u is greater or equal than 1, then we can, and let's assume that v is an interval from 0 to 1. Then we have to, we can use the formula that we derived here, but we have to substitute the value of u equal to 1. So we'll obtain f of xy at uv equal to, substituting u is equal to 1, we'll get 1 over 3v 2 plus v. So basically, this is simply, that is going to be simply a marginal CDF of random variable y. In a case when v is greater or equal than 1 and u is in interval from 0 to 1, then CDF will be defined as here we have to substitute v is equal to 1 into our formula here. So 1 over 3 u squared. Substituting 1 here, we'll get 3, so multiplied by 3. So simply u squared. Basically, this is a marginal CDF of random variable x. Now, in a case, let's assume when u is greater than 1 and v is greater than 1, then CDF f of uv is going to be equal to 1. Well, that should be all the cases. We had to do all this work here since function CDF joint CDF function shows probability that random variable x is less or equal than u and random variable y is less or equal than v. So it should be defined for all values of u and v in interval from -infinity to +infinity.